Bismillahirrahmanirrahim. So now let's look at example number 4. So the question says that an elliptical gate covers the end of a pipe 4 meter in diameter. So this is a pipe 4 meter in diameter, and then at the end there is an elliptical gate. So basically if we slice a pipe at an angle, it will create an ellipse. If the gate is hinged at the top, what normal force F is required to open the gate when water is 8 meter deep. So the water is 8 meter deep above the top of the pipe, and the pipe is open to atmosphere on the other side, and then neglect the weight of the gate. So let's first of all consider schematic diagrams of the problems. So we have water. The surface of the water is 8 meter above the pipe. So this is the pipe. The pipe is circular, and at the end of the pipe there is a gate. So the gate is of elliptical shape. So if you view the pipe from normal directions, so if I draw the axis of the pipe. So if I were to draw the pipe normal directions, this is what it looks like. So it's circular, whereby the diameter of the pipe is equal to 4 meter. So now we have the gate. So this is the gate. So as usual, first of all, we view the gate from the normal direction. So if we view from here, because the force is going to be here on the left hand side, what you will see is an ellipse. That is the ellipse. And then, so the first things that we need to determine is the center of gravity of the ellipse. So that will be our COG, and this will be our A. So then this is the COG. So our H bar is that distance there. Okay, and our Y bar is this distance here. This is our Y bar, and this is our theta. Okay, so the hydrostatic force will be acting slightly below the COG, so it will be acting there. So if I call that one F hydrostatic, so it will be acting through the COP. So this is our COP, center of pressure, and then this distance here is our YCP. So we asked to find P, the force P that we need to apply at the end of the gate in order to just open the gate, right? And then neglect weight of gate. Okay, so we know also that, so this is our H bar and this is our Y bar. So H bar is actually equal to Y bar sine theta. So first of all, let's determine FH. So FH is equal to rho GH bar A, right? So what is H bar? H bar is the vertical distance of the COG to the water surface. So we know that this is equal to 8. So halfway through here, this is equal to 2. So this is 8 plus 2 is equal to 10 meter. What about A? A is area of the ellipse. So we know that this is equal to 5. So this must be equal to 2.5. And this distance is same as the diameter of the pipe. So this is equal to 2, right? So we get the expressions for the areas for area of ellipse is pi minor axis 2 multiplied by major radius 2.5 is equal to 15.71 meters squared. So this allows us to calculate the hydrostatic force. So it's 10 to the 3, 9.81, H bar is 10, A is 15.71 meters squared. So that gives us hydrostatic force equal to 1541 kilonewton. So now let's calculate YCP. So the formula for YCP is Ixx over H bar A sine theta, right? So what is Ixx for ellipse? Second moment of area for ellipse is given by pi A cube B 4, right? So that is equal to pi 2.5 cube multiplied by 2 divided by 4. That gives us Ixx equal to 24.54. So now what about sine theta? Sine theta, theta is this angle. So this angle is also equal to this angle. So this is 4, this is 5. So sine theta is 4 over 5. So sine theta is 4 over 5. So now we can calculate YCP is Ixx is 24.54. H bar we have already calculated is equal to 10. A we have already calculated is equal to 15.71, and sine theta is 4 over 5. That gives us YCP is equal to 0.125 meter. So next, in order to determine P, so we can balance the moment about the hinge. So the hydrostatic force will create a moment equal to Fh multiplied by this distance here. So this distance is equal to this distance, which is equal to 2.5 plus YCP, and that will be balanced by clockwise moment created by P, will be P multiplied by 5. So we can balancing moment about hinge. So what we get is moment created by this force of P multiplied by 5, and this must be equal to moment created by hydrostatic force Fh multiplied by that distance is 2.5 plus YCP. So then we can get our P Fh, which is 1541 multiplied by 2.5 plus YCP is 0.125 divided that by 5. That gives us the force of 809 kilonewton. Okay, so if you recall what we did just now, we calculate the hydrostatic force, rho g h bar A. Then after that, we calculated YCP, Ixx over h bar sine theta A. So we get YCP, and finally we take moment about a hinge, and that allows us to calculate the force P. So we get P equal to 809 kilonewton. Okay, so now let me just extend the question a little bit. If the weight of the gate is non-negligible and is equal to 100 kilonewton. So if the weight of the gate is non-negligible, so we need to consider the force due to the weight of the gate. So basically, if I redraw this again, so this is the force P. Then we have the hydrostatic force. So now we will have another force acting from the center of gravity of the gate, which is equal to W. In this case, it's equal to 100 kilonewton. So now if I balance the moment again, so I balancing the moment about hinge, because this is the hinge. So I must have the moment due to the force P multiplied by 5, and that must be balanced by the moment due to hydrostatic force. So Fh multiplied by 2.5 plus ycp plus the moment due to the weight, so W multiplied by this distance from here to here. So distance from here to here is equal to 3. So distance from here to here must be equal to 1.5. So then our P will then be equal to Fh, which we have already calculated, 1541. So 2.5 plus ycp is 0.125 plus the weight is 100 kilonewton, 1.5 divided by 5. So that gave us P is equal to 839 kilonewton. So you can see that if the weight is non-negligible and is equal to 100 kilonewton, so we'll get P is slightly higher, it's 839 kilonewton. This one, if the weight is negligible. This one, if the weight of the gate is equal to 100 kilonewton.